Welcome, and thank you for joining us for Damage on the Rail, Breaking Down Impacts, including a rail shipper's perspective, brought to you by Lat-Lon, a BSM company. Our speakers today will be Dave Baker, president of Lat-Lon and aerospace engineer. Dave created the firmware generating impact G-forces, deceleration graphs, and delta velocity for Lat-Lon products reporting around the globe. And Don Loftis, principal software engineer for Olin Corporation. Don recently presented at Railway Interchange, among many other rail-focused venues. Don has also authored multiple studies on the application of emerging technologies for transportation. Before I hand it off to Dave, please note the Q&A box in the lower right-hand corner of your screen. At the end of the presentation, we will answer as many questions as possible, or we can answer offline if needed, but feel free to submit questions to our speakers. And here's Dave.
Well, good morning, everybody, or afternoon, depending on your time zone. Let's see. I want to cover the basics of the equations involved and how Lat-Lon processes the data, and then that's basically the precursor that will be needed to fully understand what Don's going to be talking about in terms of using the data later on. So let's get started. Well, before that, just thank you, everybody, for participating in this, and we'll just jump in here. So, impacts on rail. What causes accelerations in the rail environment? The things I've listed here: truck hunting, coupling rather than humping, coupling in flat yards or in hump yards, slack action, which is the motion of slack going up and down a train that's being accelerated or decelerated. Environmental factors can also create impacts. And then track events, rail seams going over a bridge abutment where the ground has settled on either side of the bridge and creates a little bump up and then a bump down. Equipment issues, flat wheel spot, and truck hunting could be categorized as well as an equipment issue where the trucks oscillate from left to right or left to right, back and forth. And then when the shipment actually is loaded or unloaded can also be a time when some accelerations can occur. All right, so Physics 101 here. We'll go through three equations that are very useful for understanding and backing out what's happened in an impact event. First one is force equals mass times acceleration. So the force pushing on a mass will cause it to accelerate. The next one is acceleration times time is the change in velocity. So delta V is V initial minus V final, or vice versa, depending on how you want to look at that. So the acceleration of one gravity, which is what we're all feeling sitting in our chairs here, is 32.2 feet per second, or about 9.8 meters per second, or actually per second squared. So what's interesting is, and a useful number to kind of keep in mind when you're looking at G's is as they span over time, that adds up miles per hour. And so 1 G applied for 1 second will cause something to start moving from 0 to 22 miles per hour. So if you jump off of a high dive, 1 second later you're going 22 miles per hour. 2 seconds later you're going 44 miles per hour, and so forth. So that's kind of a handy thing when you look at G's on a rail car and then try to correlate real quickly what kind of speed was involved prior to the coupling event. One conversion factor is that 44 feet per second equals 30 miles per hour. So miles per hour is what we're all used to, but we use feet and feet per second in these equations. Then V squared equals 2 times the acceleration times the distance traveled. So if you know the travel distance and you know either acceleration or velocity, you can get the other one, velocity or acceleration. All right, so 1G is the acceleration that is caused by Earth's gravity. And when you think about a load in a rail car, it's being pulled downward by the acceleration of Earth's gravity. So if that car has an acceleration along the track, that is added to the gravity of the Earth to create a direction of gravity or a direction of acceleration that the payload would see that isn't straight down anymore. It would be at an angle. It's not straight lateral because gravity is always pulling downward. So you can think of impacts, longitudinal anyway, or lateral for that matter, as wiggling the downward vector back and forth on the load. So once it gets angled off enough, it's going to cause that load to slide unless it's secured with straps or airbags or whatever the attachment systems might be. Now, when we look at draft gear, the amount of travel that you can provide when a car runs into another one, the more travel distance there is, the less G's there will be. So standard draft gear has about 4-inch travel or less, and you can also get cushioned draft gear, which have an oil that is like a shock absorber in it that will allow more travel distance. There's 15 and even 30-inch draft gear, cushioned draft gears. So you can see on the plot there, across the bottom is your miles per hour, and then the G's are on the left side. And so with the 4-inch draft gear, the blue line, your G's go up very rapidly as your mile per hour impact speeds go up. So the cushioned draft gear is doing just what it's supposed to do and take the G's down for a given speed of impact. So we'll just run through a couple examples here. Let's say we have a 3G impact and it was 6 miles per hour. The question would be, how long does that impact take in time? And you can see that's 8.8 feet per second. 3 G's is 96.6 feet per second squared. You run that through the equation and you get just under a tenth of a second. So a pretty quick event. And that's assuming that the 3 G's is constant the entire time. And the other question would be, well, how far was the travel distance in that situation of 3 G's and 6 miles per hour? And you use the v squared equals 2 times acceleration times distance, and you work it out 2.4 feet, which is about 4.8 inches. So these are all numbers kind of typical and representative of a rail car coupling event. You can see on this slide some excerpts from a video, 4 frames down below. So TTCI down in Pueblo, Colorado does impact testing, and these video frames were taken during testing of an auto rack down there. They were testing different chock systems to see how well they held the cars in place within the rail car. So from left to right is increasing time, and you can see the longer draft gear of the left side auto rack car. As it comes in, it compresses in, and on the right is a standard draft gear, which you can see doesn't compress in much. The other thing to note here is that the car being impacted, the one on the right, which is called an anvil car, it moves when it gets hit by the hammer car. You can see that it's moved to the right a little bit. So the change in speed of the car striking may not be its initial speed at all, or exactly, because it may push the car it's hitting. You can imagine if there's 4 cars on the left running into one unloaded car on the right, they're not going to change speed that much, and they're going to be pushing the car on the right. Now, in this test, there were several cars on the right that were the anvil cars filled with rock and with the brakes set, so they didn't move very much. All right, on this slide, just focus on the blue curve. This is an accelerometer going over a waterfall of all things, and you can see the G's go from a little over 1 and then go down to near 0, where all that wiggling starts up. So this is interesting to show that one of the interesting things you can do with our solar tracking unit with the impact detection system is if you just drop it, you'll create a 1G event, because it's going to go from having 1G to going to 0 G's, just like this plot shows of going over a waterfall. And so you can calibrate, and you can see, in fact, in this example that their accelerometer was reading over 1G when it should have been 1 exactly. This isn't a Lat-Lon product. And then when it went to 0G, you can see it went down to about 0.1, 0.15 Gs instead of exactly 0. So you can see it's a little bit out of calibration. But by dropping something, you can calibrate out those kind of errors. Now let's talk about filtering. When a rail car is in an impact, especially one without cushioned draft gear, it can be hit hard enough that the whole structure of the car will ring, much like a gong would ring if you hit it with a hammer. And so filtering is required, and the AAR has recommended practices, 803-98, on how to do this filtering, and they recommend filtering at 10 hertz. What that means is events above 10 hertz that are vibrating back and forth faster than 10 times a second are going to be reduced in amplitude. They're going to be absorbed by the filtering circuit. So the plot you can see up there shows a sine wave that's buzzing back and forth that gets dampened out. That would be the ringing, but there's also a jump up that stays steady for the first half of that plot that is at a low frequency. And so you can see the red curve, which is the filtered signal at 10 hertz, looks much more, it's got a better behavior for taking digital sampling so that we can reconstruct the event rather than just having data points all over the place. So this is the recommended practices 803-98 in text. Don't worry, I'm not going to read through the whole thing, but you can see that the 10 hertz is listed right there. And what that means is that it's at 10 hertz, you'll be attenuating it by 3 dB, which is roughly half the strength of the signal is getting through at that point. As you go up in frequency, even less of a percentage of the signal can get through the filter. Now, they go into all kinds of detail about how it should fall off. In other words, how quickly should you attenuate the signal as you increase its frequency, and I won't dive into all that right now. 803-98 was written to support the auto rack projects, and basically when you're worried about ride quality monitoring, the AAR is assuming that you're in a cushioned car to begin with. Otherwise, why go to all the trouble of worrying about impacts when you don't even have the right draft gear on the car? So the 10 hertz is a nice kind of a slow number. It's not as aggressive as it could be for these cars because the squishy draft gear on them allow the events to take quite a bit of time, relatively speaking. Now, we found that there are people who want to see what the environment is like without cushioned draft gear, which means the impacts take much less time and the Gs are much higher. So what Lat-Lon offers with the STU solar tracking unit with impact is two different filtering rates. So we have 10 hertz and 100 hertz. We actually sample the data at 500 hertz, but we have different options for you. You can actually change whether it's 10 hertz or some other number, but we provide 10 and 100 as our baseline starting points. Let's see. I think I'll skip all the math there. We've done enough of that, and I don't want to steal too much of Don's time here. Let's talk a little bit about delta velocity. When you look at the area under a curve of acceleration, that area is proportional to how much change in speed you're going to have. So in the plot there, the green curve is the delta velocity. It's how much speed this vehicle must be accumulating based on the acceleration that's incurring. And so if you integrate the area under the curve of our accelerometer plots, you can get the change of speed that occurred in the impact. The reason we're interested in delta velocity is because that's what railroaders know about. They know what speed their locomotive's going and what speed they're running cars down into a basin at a hump yard. And their rule, their goal is about 4 miles per hour to keep the coupling events at that speed or less. Oftentimes they get up a little higher than that. If a wind gust comes along behind the car, it'll accelerate it, especially if it's a big car like an auto rack, if it's empty especially. So we're interested really in coming back to saying, well, how fast did that car couple? So at Lat-Lon, we're putting all of this together in our Stew with Impact product line to give you the GPS data, the accelerometer data, and the speeds before and after the impact. One thing we have is what we call a deceleration alarm, where we're looking at the speed of the car, and when it suddenly goes down, we can report what speed drop that was. And that's something you can take to the railroads and say, hey, because of our GPS, we were in this yard. You can see that the impact happened in the bowl, and you can see that the speed dropped by, say, 8 miles per hour, and that's something that they can deal with rather than saying it was 3.6 Gs. So here's some plots of yard impacts showing where they happened in the yard on uncushioned draft gear. So you can see there's a lot more ringing energy in the 3 plots. The red curve in each of these 3 impacts is the longitudinal direction, and the kind of yellowish curve, gold-colored curve, is the vertical, and the green is the lateral. So you can see there's area under the curve on that red acceleration curve, which is the change in speed, and then you can see all the excitation, the ringing back and forth of the whole structure from the energy of the impact. Okay, and at that point, I'll turn it over to Don.
Thanks, Dave, and thanks to Progressive Railroading and Lat-Lon for the opportunity to share this information. Much of what we're focused on really relates to improving safety and security, and the reason Olin lets me take advantage of these opportunities is, we believe that it benefits everyone, the railroads, the shippers, the customers, to share practices around safety and security. Olin's primary goal in their track and trace program is to create the most comprehensive record we can on every single shipment. Just a brief word about Olin. Olin has several divisions: Winchester Ammunition, KA Steel, and chlor-alkali products. And recently, as part of chlor-alkali products, we acquired Blue Cube's chlorinated products from Dow Chemical. So we're really the largest global manufacturer and shipper of chlorine caustic in North America. And we, because of our geographic coverage, we touch all Class I railroads. So as part of our goal to create the most comprehensive records we can on every shipment, we have our fleet equipped with several thousand GPS units from a couple of different vendors. And we mount them on rail cars as shown in this diagram. And I think the location of your GPS unit is important. As David mentioned, sometimes a force is concentrated, especially in an undamped system, and those forces may not propagate fully down to your GPS location. So a car can be struck on either end. Ideally, having the GPS positioned in the center of the car may be the best way to ensure that you equally detect impacts from both ends. However, with any decision, there's a trade-off, and the reason for the distance difference in our Lat-Lon units is they contain cameras, and we wanted a wider angle of view so that we could see the platform and the ladder really well. And we also placed the units outside the platform area to avoid the damage and tampering possibilities. We found that it's most important to be consistent with GPS placement, and that way you can do comparisons with other impacts on other cars. Really, we use our data from the GPS units primarily for 2 purposes. One is ride quality, and the other is security. We have several thousand GPS units, and all of them have accelerometers in them. And they detect 3 axes of accelerations in Gs, the X, Y, and Z. That's side, forward, backward, and lifting. So some data, some report data, actually the Lat-Lon units give us both the 10 hertz filtered values and the fast 100 hertz filtered values. And I'll talk a little bit about that in a moment. And we also have those independent techniques to measure velocity changes. So one is an accelerometer-based velocity change. Acceleration is a change in velocity over time. And you can integrate that and get miles per hour velocity values. And the other is a more direct approach. GPS can measure speed at very short intervals. It's also quite accurate. I think it's less than 0.4 miles per hour. And so, you know, you can take a reading of your speed now and a reading 2 seconds from now and subtract the difference and get the deceleration speed. So what I did here was I moved this slide up quite a bit because I was afraid I wouldn't be able to complete all my slides, so I wanted to get this conclusion slide up front. This is based on our experience. You know, we've seen cars that have experienced 10G impacts and showed no damage, and we've seen cars with 5G impacts that had busted couplers, and we were wondering why. So essentially, over time, we've developed the following criteria to mark a car as needing inspection to look for damage. And what we look for is short duration, high impact events that last less than 50 milliseconds. Again, this is important to know both the 100 hertz filter reading and the 10 hertz filter reading to be able to determine the duration of your impacts. We look at overspeed events. These are GPS-based deceleration events. We look for undamped or vertical or side events, and then we mark these cars for inspection. So this shows what we would typically expect humping to be like. We took a Trackmobile delivered loaded car and released it at 5 miles per hour, and it rolled into 6 cars that happened to be on a cushioned anchor. And what we see is that the 10 hertz reading and the 100 hertz reading are equal. And what that tells us is that the event took a significant amount of time, at least 100 milliseconds of time. And that's a nice, gentle, dampened, non-shock type event. So this is another event. This is a derailed event that caused some skin damage. And in this event, it's more of a shock pulse type event. And what we're doing is we're taking the 100 hertz readings and subtracting from them the 10 hertz readings. And that gives us, in this case, a 5.5G lateral impact. So seeing a difference between the 100 hertz filtered readings and the 10 hertz filtered readings tells us that it was a short duration impact. And that means that all that energy was coupled into a very short acting event. And because tank car skins are relatively thin, they're vulnerable from the side. So this car gets marked as one that we want to inspect, and turns out that it did have side damage. So this shows a longitudinal impact of 6.4G, 6.6 miles per hour. And again, this is a shock pulse type event. If you take a look, we see the 100 hertz reading at 6.4 and the 10 hertz reading at 2.5. So we know that this event happened in a very short period of time. A lot of energy was focused on the coupler. And as a result, we see when the car gets back into our yard that it has a dislodged spring due to a 3G lateral impact. So what do we do with this impact data? In addition to marking the cars for damage when the car gets back in the plant, we can also analyze where in the railroad system impacts are happening. We use this tool to look at impact data through the whole system. So it combs through the data based upon your selection and determines the top 10 yards where the most number of impacts occur. And we can also look at the percent likelihood that a car moving through a top 10 yard will experience an impact. And it will also let you view the average impacts G value for these top 10 yards. That's a profile. And that's what you see in the bottom chart here. In this case, we saw 28,400 impacts over 3 Gs with an average impact of 3.6 Gs. And when you look at the bottom chart, this is a profile that shows you that the 2 and 3 G events were by far the most common impact events. And then it starts tailing off at 4 Gs down to 11 Gs. And this is exactly what you would expect when looking at the individual yards. You would expect them to have this same profile. And we do for almost all the yards, especially all the hump yards, which for the most part have pretty good control. However, there are exceptions, and these most often happen in flat yards. So you're allowed to look at the average G force per yard. And when you do that, you see that yard number 8, in this case, when I click on yard number 8, I see that it doesn't have a normal yard profile. That about 10% of the impacts in this yard are 10 Gs, which is really high. And that 65% of the impacts are 5 Gs or higher. So this particular yard would be a candidate for us to take the data and give it to the railroad that owns the yard, and hopefully they will fix the problem. Well, the second technique to determine ride quality is to look at the coupling speeds, the hump speeds, if you will. We use a straight forward approach for that. GPS units are pretty accurate at determining speed, so every couple of seconds while the car is in motion, speed changes are gathered, and if the speed changes between these readings, then you have a coupling speed or a deceleration speed event. And we can determine the original speed by looking at the final speed reported, and that's the values we see, original, final, and speed drop. And we also get really good correlation between the delta V readings from the accelerometer on the GPS and also the speed drop readings as calculated by subtracting speeds. So we can analyze the GPS speed drops or coupling or hump speeds in the same way that we analyze the G-force accelerometer data. We can look for the top 10 yards in the country that we've seen the most number of deceleration events. And in this case, we can look at a percent likelihood that a car will experience a 3.5 mile per hour coupling event or higher in any one of these yards. And I can tell you that in yard number 3, there's a 12% chance that a car will experience a 4+ mile per hour deceleration event. So again, by looking at a yard's hump speed profile, you can get an idea of what might be happening. In the bottom left-hand corner, you can see that in this particular, this is a hump yard, that we see a nice profile for deceleration speeds. It's the vast majority are about 4 miles per hour, and then it tails off down to 9 miles per hour. But if you look, you see that it jumps up to 10 miles per hour. It's almost, I think, 70 or 80 events that were 10 miles per hour deceleration speeds in this yard. Well, we have the ability to look at and see exactly, because it's GPS, you see exactly where these events were happening. And in this case, we could tell that the 10 mile per hour couplings were actually occurring in the feeder or flat tracks above the hump yard and not in the hump yard. So to prove I'm not a competent scientist, I like to show this slide when I get a mass audience in hopes that someone can explain it to me. Here are all the deceleration events that I've measured starting in 2011, going through October of 2015. And I can see that the average coupling speeds in 2011 were steady around 4.8 miles per hour. And in 2012, it rose steadily to almost 5.6 miles per hour. Then it tailed off and steadied out about 5.2 miles per hour in 2013 through today. So this data represents hundreds of thousands of data points, and I thought it might be correlatable to maybe an increase in car loads, but honestly, I just don't know. So if any of you would like to propose correlations, and especially if you can point me to data for a potential correlation, then please email me your thoughts on this. So as I've mentioned, we use GPS primarily for two purposes. One is ride quality and the other security. GPS are wonderful devices that you can attach a lot of different sensors to. Accelerometers is one type of sensor, but there's others such as gas sniffers and so forth. However, the barrier to implementing sensors is really a fear of false alarms. So if I get an alert on a rail car and I initiate an action, and that causes the train to be stopped or a community to be evacuated, and it was a false alert, well, that's a significant cost to the railroads and to us. If it wasn't a false alert and I do nothing, then that's a significant liability because I should have done something. So what does it take for me to believe an alert? And the answer was I really wanted to jump in my truck and drive down to where the event happened and see for myself, but I can't do that. So it makes a lot of sense to equip GPS devices with the ability to take images. And with images, you know, you can get context. You can tell if a car's been derailed, for example. In this case, we ask the GPS to take an image whenever there's a deceleration event greater than 5 miles per hour, whenever we see impacts over 5 Gs, whenever someone opens the valve dome while it's in transit. And we're really just piloting this motion detection, but the idea here is around tampering. And of course, you can manually request an image to be taken. So I'm Olin's Rail Security Coordinator, and what I do every morning when I get a summary email that contains the images from the previous day, and I'll thumb through these images looking for cases where maybe a dome lid's been open while the car's been in transit, and I can tell by the image whether the person's wearing a hard hat or not. And if they're equipped with a hard hat, they're likely rail inspectors. If they've got a do-rag on with a wrench in the back pocket, maybe this is something that I would report to the Fusion Center or TSA. So I've already mentioned most of these abnormal ride quality events, but I did want to say that what we do when a car is in transit is we collect these alerts, these high G alerts, these deceleration event alerts, security, but we also tap into the USGS and get earthquake information and we get early warning and maintenance advisory and acoustic brake detector information and truck hunting, wild equipment health alerts, DDCT, and wind. And we report all of these alerts back to the loaders when the car gets back into the plant and ask them to inspect. This shows a derailment event that happened back in 2012. You can see that it was a slow occurring event. If you look in the picture in the right-hand side, this was returned to us within 3 minutes of the derailment, and you can tell that the trees are horizontal and not vertical, and that's not normal. So the car is definitely on its side. If you look in the right-hand side, the picture there is just blown up and rotated at 90 degrees. You'll notice to the left of the word dome, there's a round white image that indicates that the dome lid had come open in this derailment, but you can also tell that it doesn't appear that there's any product leaking. So images are really helpful. You can see this is a 7-mile-per-hour 5.5G vertical impact, and you can see by the blurriness of the image that it definitely lifted the rail car. On the right-hand side, it's a 4.9G lateral impact, and the car almost tipped. This just shows how we do weather tracking. We document all of our trips via Google Earth Flights. We generate a movie, so it gives you a bird's-eye view of the trip that the car took. It changes the camera angle and raises the altitude of the camera based upon the distance between readings. And if any of these things on the left-hand side, such as impacts or deceleration events, or we have images, it will stop, pause, and pop up with a balloon help that shows you information about that. So this is my final slide. What's Olin's intent? What we're doing is we're sharing a railroad's data set with that railroad. We do not share Norfolk Southern's data with CSX or the public for that matter. And our hope and belief is that the railroad will take and use the data to fix their issues. We avoid reporting individual events to the railroad. That's a cry wolf issue. If we did that for every single event, then they'd quit answering our phone calls. Instead, we like to share results about systematic problems. And Olin is a ORC member, responsible care member, and with that comes the concept of caring about your product from cradle to grave, and it can't get there without going through some form of transportation. So our hope is that we can explore techniques to prevent tampering. We want no Olin equipment to contribute to any sort of derailments, and we want to strengthen relationships with industry partners and share this information with other shippers whenever we can. So thanks.
Thanks everyone for attending today, and with that we'll conclude